Combined heat and power. Combined heat and power, CHP, also known as cogeneration, is the generation of heat and electrical power from a single fuel source. In this presentation, basic concepts of CHP are discussed, which include a general process description of combined heat and power, the types of equipment that are used to generate heat and electricity, electrical efficiency, electric and thermal load profiles, basic CHP selection rules of thumb, permits and pollutants, and lastly, fundamental CHP economic relationships. The general process of combined heat and power converts fuel into electricity. Then thermal energy from the generation process is recovered, and that heat is used to heat buildings and, through the use of a device such as an absorption chiller, also cool the buildings. In the diagram below, fuel is used to operate, in this case, a gas turbine that's coupled to an electric generator. The heat in the turbine exhaust is recovered in a heat recovery boiler. That generates either steam or hot water, and that is transferred or piped to the building, where it's used to cool the building or heat the building, and also in cases of cooling, it's used for reheat purposes during the summer months. Electricity for cogeneration is produced using various types of equipment. Gas turbines, which are very frequently used, are a piece of turbo equipment that is also an internal engine, and it's to be differentiated from a steam turbine, which runs on steam alone. Also used are reciprocating engines. These are engines that can be small or large, very similar to a car engine. Steam turbines, which take high pressure, superheated steam. It has to be superheated in order to remove moisture so that the water droplets don't corrode away the turbine blades. Combined cycle, which is a gas turbine that's used along with a steam turbine. The gas turbine exhausts, recovers heat, which generates steam, and the steam is then used to drive a steam turbine. And fuel cells.
A key first step, even though it may come at the very end of the process, is to provide the microgrid development with a name. The name should be simple and clear, such as the town name and then community microgrid. In the case of Neptune, the community chose to name their project the Neptune Township Advanced Microgrid, NTAM.
Gas turbine. A gas turbine has an electrical efficiency, as we previously stated, around 33%. In the picture below, normally the electric generator would be coupled to the gas turbine at the shaft, and that's referred to as a genset. The compressor section raises the combustion air pressure from atmospheric pressure up to a compression ratio of about 10 to 1, so that would be 147 pounds per square inch. Fuel is then injected into the combustion chamber and ignited. In order to inject the fuel into the combustion chamber, it must overcome the pressure of the combustion air, which at this point is 147, 150 pounds thereabouts. The gas pressure of the fuel has to be higher than that of the combustion section in order to get the fuel into the combustion section. The combustors in the turbine are sometimes referred to as combustion baskets or burner baskets. The turbine section converts the energy from the hot expanding gas in order to turn the shaft. The reciprocating engine. Reciprocating engines have an electrical efficiency of about 40%. They vary in size. They can be small, 100 horsepower and even smaller, to several thousand horsepower. The engine itself is similar in concept to an automobile or truck engine. It has pistons that go up and down or back and forth. Heat can be recovered from the exhaust of the engine and also from the cooling system that cools the engine block. However, the exhaust temperature is generally much higher than that of the cooling water. The cooling water has a temperature somewhere in the range of probably 180 degrees. So that can be used to generate domestic hot water in cases of buildings where they're close, 180 degrees can be used sometimes to heat the building. However, to drive an absorption chiller, 180 degrees is probably not sufficient temperature in order to drive an absorption chiller. The fuel used is generally natural gas. Diesel fuel can sometimes be used, but it may be prohibitive for environmental permitting reasons. Steam turbine. Steam turbines have two basic types, a condensing turbine and also back pressure turbines. A condensing turbine, which has a higher electrical efficiency, has a heat exchanger that condenses the steam that's leaving the turbine. A back pressure turbine, also known sometimes as a topping turbine, has lower pressure steam that leaves the turbine. Condensing turbines, as I stated earlier, have a higher electrical efficiency and can range anywhere from 20% for smaller turbines on up to 38% for very large, efficient turbines. Back pressure turbines, on the other hand, have a relatively low electrical efficiency and range somewhere between 7 to 20%. Steam turbine base plants are generally more expensive than gas turbine or reciprocating engine base plants. Combined cycle. In a combined cycle plant, the gas turbine drives a generator, and the exhaust, indicated in red in the diagram, is used to make steam in a heat recovery boiler. The steam from the heat recovery boiler, which is shown in light blue, is used then to make more electricity with the steam turbine. In this case, it's a condensing turbine. The steam exhaust from the turbine is condensed back to water in a heat exchanger, generally called a surface condenser. Combined cycle plants have an electrical efficiency of around 50 to 60%. They are also relatively expensive. The fuel cell. A fuel cell is an electrochemical device that converts fuel, again, the fuel of choice generally is natural gas, into electricity. Fuel cells are a relatively new technology with many evolving advancements. Fuel cells have an electrical efficiency of between 40 and 60%, depending on what type of fuel cell they are. The phosphoric acid fuel cells, PAFC, comprise the largest segment of the existing CHP products worldwide and can provide electrical efficiencies around 45%. Molten carbonate fuel cells and solid oxide fuel cells are also used for combined heat and power and have a higher electrical efficiency, around 60%. Disadvantages of fuel cell cogeneration systems include slow ramping up and down rates. And what that means is that if the electrical demand is going up and down and you want to follow it with the fuel cell may have trouble adjusting rapidly enough to meet those demands. And they are higher cost with a shorter lifetime. Heat recovery boilers. Heat recovery boilers are covered here just so you get a sense of what device is used to recuperate the heat from the generation process. Boilers of this type can generate steam. Also, in some cases, they generate hot water, high temperature hot water in many cases, by extracting heat from the exhaust of a gas turbine or a reciprocating engine or even a fuel cell. The heat recovery boiler is similar in concept to a regular boiler, except that it's not equipped with a burner. Hot exhaust passes over water-filled tubes and it produces steam. Absorption chiller. Absorption chiller is included, again, to show how air conditioning can be made from heat. Seems counterintuitive to make chilled water from hot water, but that's exactly what it does. The absorption cycle uses heat-driven concentration difference to move refrigerant vapors, usually water, from the evaporator to the condenser. The high concentration side of the cycle absorbs refrigerant vapors, thereby diluting the solution. Heat is then used to drive off these refrigerant vapors, increasing the concentration again. Lithium bromide is the most common absorbent used in commercial cooling, with water used as the refrigerant. Electric load profile. Electric load profiles for facilities to be powered from CHP plants are modeled from utility data on a daily, monthly, and annual basis. A rough approximation of a weekday profile of electric power consumption in a typical commercial building, depicted below, resembles a bell curve. The usage increases morning to afternoon and then decreases in the late afternoon. The lower curve depicts a weekend day. The evening hours and weekend loads are referred to as the base load. Weekday afternoons are typically when peak loads occur. Interval electric load data can often be obtained from the utility. If the utility is contacted and you request it, many times, depending on the type of service you have, but if you certainly have HTS, in some cases LPL, large power lighting, the utility will actually furnish you interval data indicating over time what the electric load is at a given point in time during each day. Thermal load profile. The thermal load profiles for the facilities to be served from the combined heat and power plant are also modeled on a daily, monthly, and annual basis from utility data. The utility data being, in many cases, most cases, it's a gas meter. If the buildings run on oil, then it would be meter readings during the course of the day that would indicate what the load profile is. Some people would use steam charts to do that. However, it's probably not recommended because steam's very difficult to actually measure when there are variations in flow. So generally, for thermal load profiles, gas meter data is used, and that indicates how much gas is being used over an hour at a particular point in the day, and those vary, again, with time of day and the day of the week. The thermal load profile depicts demand over a period of time and the quantity of heating and cooling energy that must be added or removed from the building to keep people comfortable. The graph below shows average daily loads plotted hourly during the months of January and March. When selecting the type and size CHP plant, there are some rules of thumb that generally apply. The first one is that 3/4 of the available recovered heat should be utilized. Now that's always a challenge because what do you do with the heat during the shoulder months, during the spring and the fall? Generally, for the feasibility economics to work, you need to recuperate and use that heat close to 3/4 of the time. Now there may be exceptions to that. Obviously, if there's a big spark spread between the price of natural gas and electricity, the economics can work with recovering very little heat. Over time, in general, however, it's better to utilize, both from an environmental standpoint and a financial standpoint, as much of that heat as you can. But there will be trade-offs there between generating electricity during peak periods and actually utilizing the heat that's generated. The sale back of electric power to the utility grid, that is the local distribution company, generally is not cost effective. They will pay something, but it's usually not enough to cover the cost of generating the electricity. Often, it's not economic to make all of the electricity or all of the heat required to satisfy the entire load of the facility. There are strategies such as electric load following, thermal load following, base load following, base thermal load following. There are different scenarios used operationally to blend the production of electricity and heat in the most cost-effective way. Permits and pollutants. Air permits are generally required for a CHP plant. Small plants may have a very simple permitting process that just requires filling out some paperwork and having a fairly short approval time. Larger plants, however, it can be quite complex. If the plant does not meet certain requirements, it can necessitate the need for a so-called PSD permit, Prevention of Significant Deterioration, which is a lengthy process and does take a considerable amount of time. NOx, nitrous oxide, and SOx, sulfur dioxides, and particulates, regulated pollutants. Those are used in the permitting process, and the levels of those made are generally incorporated into the permit conditions. Again, the permit itself can be complex. If the cogen operator is required to have a Title V permit, there are various reporting requirements. It has to be recorded every time the plant started up and shut down. The annual fuel usage has to be accurately reported every year, things like that. CO2 is not a regulated pollutant, however. There's been legislative moves in the past to try to regulate it, but it's a very contentious subject, and so far, CO2 production has not been regulated. Although fuel cells don't emit NOx or SOx, they do emit CO2. So one of the advantages of fuel cells is that it's said they don't pollute, and that's true in the case of NOx and SOx. However, they still do emit carbon dioxide. CHP can reduce overall CO2 emissions if you take into account the displaced CO2 that's emitted by the utility during the generation process. CHP Economics. The economics to support the construction and operation of a CHP plant are often driven by the comparative cost of buying electricity from the utility, along with the cost of boiler fuel, referred to as the base case, measured against the cost of fuel, supplemental purchased electricity, and the incremental operating cost of the CHP plant. In simple terms, it's the cost of the electricity and heat before CHP versus the cost of electricity and heat with CHP. And it's that cost delta that determines the savings. The selection of type and size of CHP plant depends heavily on the degree to which the electric and thermal load profiles coincide with the facility's loads being served. This means that as you generate electricity at a particular level, it will also generate a certain amount of heat with that level. Those levels need to match the loads as closely as possible to what the requirement of the facility is. And lastly, a feasible CHP plant can be expected to save about 15 to 20% compared to purchasing utility power and fuel. That equates to somewhere between 5 and 7 year straight line payback. Thank you very much. My name is Paul Meyerdirk. If you have any questions, please feel free to contact me at pmeyerd, MEIERD, .source@gmail.com.